let's start our business. Before starting today's main topic, I'd like to give you a bit more details on the calculation of computer ratio. So last week, we studied the K-server problem, and I show you its comparative ratio. But unfortunately, I didn't have much time, so the last part of the class might be kind of hasty. Okay. So the idea is to use a amortized cost. That is equal to real cost at step I plus plus some function psi and the difference of the value of psi between steps I plus I and I. Okay, this is amortized cost. And for this problem, of course, we need to select this function psi carefully. But in this case, we use this function. Okay, I'll show you. So we have two configurations, two positions of servers. This is arg. It's opt. And maybe, I don't know, something like this. Okay. Okay. So we consider matching between arg servers and opt servers. This M means the size, total size, the sum of the lengths of matching. That means this is the length of matching, and the length of matching, the length of matching, and this is them. Okay, so M is the sum of those lengths of matching. Sigma DC means what? Sigma DC is the sum of lengths of all pairs of arg servers. Okay, so this is a function psi. Now, at step I, we have a request here. Suppose that we have a request here, and suppose that this opt server moves here. Okay, then okay. That's all right. Okay, all right. Okay, so this server moves here. Well, this is DI. This is the cost of the opt. Okay, now the matching. Now the current matching is this. Oh, here. This, and now arg server moves. By the rule, arg server moves like this. Okay, so this server moves to the requested point, And this server also moves the opposite direction, the same distance. So that means this is Si over 2, and this is Si over 2. Okay? Now, by moving this, this di, delta phi is at most k times di. Note that this is the cost. Delta phi is a part of the cost. That means the smaller the better for us. That means we'd like to bound this delta psi from above, right? Because the smaller the better. In this case, obviously, this matching increases. Actually, this is not exactly increasing. But suppose that this server is like this, then exactly this matching increases, okay, by at most di. That means we have a coefficient of k, delta psi increase at most k times di. And what is delta m? What is a change? What's the change of matching? The change of matching is, this is at most 0. Why? Because it's pretty easy, by moving from here to here, this matching decreases exactly this value, Si over 2. This matching like this to this, then this matching becomes 0. What means it decreases at least Si over 2. And don't forget that this server also moves the same distance, so it may increase. The matching may increase. Actually, this matching increases. This matching increases by this value, but because of this minus value, the total increase is at most 0. Of course, for other matchings, there is no change. There is no change. Okay? And what is delta sigma di? This is exactly equal minus Si. Why? Because this pair decreases Si. So minus Si increases minus Si. Okay, because this pair just shrink. So the decreases by this value. And for other pairs, this move and this move all cancel out. So exactly this value. That's why delta psi is at most kdi minus Si. Okay? And, it is amortized cost. So amortized cost equal algo I is Si plus k di minus Si is equal to, at most kdi. So this is enough for us. If the amortized cost is k times the cost of opt, then the competitive ratio is at most k. Good. Of course, there's another case that is, the request is coming around here, but that is easier. Okay. However, this analysis is not complete. this analysis has a small hole. Why? Because there are different cases. They're different case. Okay, so we have okay. And I said that this server moves. I said this server moves. But why not? Why not moving this server? Maybe opt, move this server. I don't know. That I don't know this, how opt, select a server. So maybe this guy might move here. Then what happens? Then, okay. Okay, then now we don't have the server, and the server comes here. Then what happens? The matching this, matching changes like this. Now, the problem is if two server moves like this, then the both matching increases. Now this matching increases from here to here, this to this. Okay? Both matchings increase. So no, this is not good because we'd like to have this formula. Okay? But in this case, it's the previous case, this matching decreases. This maybe increases, but this decreases. Definitely decreases. But in this case, both matching increases. Wow. It's bad. It's very bad for us. But be careful. Now we can change this matching like this. Or this matching cross. This matching crosses. Okay, in the matching crosses, then we can always change the matching so that they don't cross like this. Okay. Then the value of matching is obviously decreases. Like the previous matching is like this. The sum of the value is like this plus this. But it's obviously larger than this plus this. Black matching. Okay. So if this server moves, then we can change the matching from blue to black. Then the value of matching does not increase. Actually, it decreases. And then we can use exactly the same argument as before. Okay? So our analysis is also correct in this case for any opt server that's moving. Okay, good. Okay, so this is a small, this is a recap of the previous class. And I'd like to go to a new chapter. Okay. So now, chapter 1, the basic techniques. Chapter 2 was, yes, online algorithms. And now we are going to chapter 3. Chapter 3 is for approximation algorithms. Okay, so we are now starting a new chapter. Approximation algorithm means exactly, as literary meaning. I'll show in a moment. Okay. So let's remember. Three-sat problem. The problem three-sat. We are given formula F. Boolean formula F like this, and the question is the question is F satisfiable? The question. Satisfiable means by some assignment, some truth-false assignment, 0-1 assignment to variables, we can make the all clauses true. Okay, that's the definition of satisfiable. And this is an NP-hard problem. Meaning probably we don't have polynomial time algorithms. Probably. I didn't tell you the details of NP hardness, but if a problem is NP hard, then it's a good, it's a good evidence that we don't have any efficient algorithm. Okay. But we do have a naive approach, of course. Trivial algorithm. That is, of course, to check all the assignments to the variables. If we have n variables, then all 0 through all 1, that is, 2 to the n different assignments. That means we need 2 to the n steps, and this is not so good. For example, 2 to the 100, if n is equal to 100, then okay. 2 to the 100 is something like 30 digits. 30 digits. This is too much. This is too much for any computers. Okay. So we can't do that. definitely it's impossible. Okay? But fortunately, I told you that we have a nice approach. We have a nice algorithm that based on local search. Then the complexity decreases to 1.334 to the n. Okay, 1.334 to the n. Then if n is equal to 100, then that is something like 10 to the 12. Yeah, this is just manageable by this today's computers. Just your laptop. Your laptop is very quick. So 10 to the 12. 10 to the 12, that is a billion? I don't know. Billion, no, trillion? Maybe trillion. I don't know. But anyway, this is possible. This is possible for your laptop. But if n is equal to 200, then the value jumps up to 10 to the 24. It is impossible. It's totally impossible. Yeah. So that means that means obtaining an exact solution. If I say a solution, that usually means exact solution. Exact solution means correct solution. Exact solution is hard. In this case, exact means exact means just depending on the definition. Solution, exact solution means that satisfies all clauses. That satisfies all clauses. Okay? So this is not easy. This is hard. But what about obtaining an approximated solution? Approximated solution. What do I mean by approximated solution? Okay. For example, I mean by approximated, satisfying at least 85% of the clauses. Okay, that is what I mean by approximated. Well, satisfiability is very important. It has a lot of applications. So, for example, we can make a class schedule. Okay, your class schedule. So Monday morning, you have this class, and then the next slot, you have, I don't know, artificial intelligence, and so on and so forth. in this lecture room or in that lecture room. So that's the class schedule. Designing a class schedule, we can use this satisfiability. So, the class schedule has a lot of constraints. For example, if some of you would like to take both algorithms and AI, then those two classes, should be assigned to different time. Okay, and also, this algorithm is very popular, so we need a big classroom. Actually, we don't need a big classroom, but for some course, we have this big room, and for this classroom course, this big classroom, and so on and so forth. Okay, so we have a lot of constraints, and those constraints are usually given by clauses. Okay, so now solving the satisfiability of the formula, if that is the exact solution, then it satisfies all, it clears all the constraints. That means all people are happy. All people would be happy, for that class schedule. What does it mean? If your assignment, your solution satisfies 85% of clauses, that somehow means 75% of the people are happy. It's something like that. So 15, the rest of the people would not be happy. For example, if I'd like to take both algorithms and the databases, but two classes is assigned at the same time. I can't take both. Okay? That means the remaining 50% of the people would not be happy. But, well, in this world, there is no completeness. So maybe 85% might be okay. So that is the idea of approximated solution. Okay, is that clear? Good. So let's call this problem SAT prime. Let's call this problem SAT prime. Okay, now there. We do have a polynomial time, very efficient algorithm for SAT prime. The original SAT is difficult, but for this problem, SAT prime, it's pretty easy. We do have a polynomial time algorithm for SAT prime. Proof, okay, proof is just one line. Okay, our algorithm is just one line. Just create a random assignment sigma and make it answer. What is random assignment? Random is just use the die, and for x1, you randomly choose true or false. x2, randomly choose true or false, and so on and so forth. And just output that assignment. There's the same, this is just single line algorithm. It's pretty easy. Why this is correct? Why this is correct? This is again very easy. So for example, x1, stuba. This is the first clause of that formula. Is satisfied. Sorry. Satisfied. Okay. The first clause of F is satisfied by this assignment sigma with probability 7/8. Why? Why? Because this clause is not satisfied. It's not satisfied by sigma with probability 1/8. Because not satisfied means false, false, false. Okay? False, false, false. But this guy becomes false with probability 1/2. This guy becomes false with probability 1/2. 1/2. Okay. So the first clause is satisfied by sigma with probability 7/8. That means of course, the expected number of satisfied clauses by sigma, by assignment sigma, is, of course, 7/8 multiplied by the number of clauses. And this value is 0.875. Okay? So that means sigma is this assignment sigma is a correct answer with high probability by Markov inequality. Well, this expected number is greater than our required value, 85%. This number is greater than our requirement. Then by Markov inequality, our solution is correct with high probability. Great, great. So this is exactly approximation algorithms. Okay. Okay, so approximation algorithms, we have two requirements. Number one requirement, they run in polynomial time. Our motivation of introducing approximation algorithms is, of course, we want to save time. We can't spend too much time. That means approximation algorithms must run in polynomial time. This is the first requirement. The second requirement is, of course, a guarantee. Okay. Guarantee quality of their solution. Okay. So of course, we need some measure. We need some measure for the quality of solutions. Okay. Actually, we did the same thing for online algorithms. In the case of online algorithms, the quality is given as a competitive ratio, right? Okay. Now we introduce the same thing, almost the same thing. Okay. Oops. Something is strange. Oops. Ah. Okay. Oh, okay. I'll show you this this measure. So, just I want to give you one example. It's a very famous example of a scheduling problem. That is bean packing. Bean means, bean means overhead bins of airplanes. So just something like a container. Okay, something like a container. Input. So this is a one-dimensional model. One-dimensional model, usually, being container is a two-dimensional or even three-dimensional. But to make things easy, we are now considering one-dimensional version of a container. So input is value, just a number. We call them items. So our input is just a set of items. That's just a number between 0 and 1. A problem. Okay, the problem is you have to pack all items into bins of size 1. So items is just like your luggage. So you have to pack all your luggage into the bins of an airplane. That is exactly this problem. Our goal is, of course, minimize. Minimize the number of required bins. Okay. Simple example. Simple example is one, two, three, four, five, six, seven. Okay. So simple example, we have 7 items. We have 7 items. We need to pack all 7 items into bins of size 1. This is a bin. Okay. First bin, we put of size 1. So suppose that we put this guy into this bin, then this is 0.5. And the next one, this guy, then the 0.35. Okay? Suppose that we put this guy bin and this guy into the same bin, then there's no enough space for a third guy, right? Okay? Then we need a new bin. And we need one more, right? Because just look at those remaining 5 items. The total sum of the remaining 5 items is obviously more than 1. That means we need another 2 bins. Okay? So this is one solution. One solution. Do you have any different solution? Our goal is, to minimize the number of bins. For this solution, we need 3 bins. So the question is, if we have 2-bin solution. Of course, yes. If we put, I don't know, 0.5, and so this guy, and this guy, and this guy. Okay? Then all the remaining guys, for example, this one, and this one, this one, this one, can be put into a single bin. So we need only 2 bins. Okay. That means this answer is better than that one. Actually, we obviously need, it's impossible to put everything into 1 bin. So this solution is optimal. Again, exact solution is hard. If you are interested, then you can read some textbooks or maybe some web pages. Then it is very easy to find the solution, find the proof that this problem is NP hard. That means if you really try to get optimal, the best solution, then it is hard. It is hard, not easy. Of course, this is a small example, so it's pretty easy to obtain this best solution, optimal solution. But just imagine that you have 1 million items, 1 million items, and that's totally impossible to obtain absolutely, exactly optimal solution. So this is NP hard. Now, I'll show you, of course, I'll show you an approximation algorithm. our algorithm is called first fit, FF. Okay, just we pick. We consider, we look at items I1 through IN, one by one, in the given order. We don't care the order. Okay, just the given order. Okay, number two step. Step two. Now we are looking at IJ. Now we are looking at IJ. Okay. And also suppose that we have k bins. We have now k bins are open. Open means we are already using those bins. Okay? We are already using those bins. B1 through BK. Then put okay, so this is our strategy. We are now oh, sorry. I made a mistake. This H. Okay. So once again, suppose that we are now using k bins, B1 through BK. Then the current item IJ is put into some bin BH, such that BH is now available. That means space. Enough space for IJ, and any BL is not available. Any BL means, L is less than H. So it's the previous bins. The previous bins are not available. That means BH is from looking, from looking from left to right. Then this BH is the first bin which can accommodate the current item ij. That is our algorithm. Now it's pretty easy. Pretty easy. Is it clear? So look at, now we are using these bins, just looking at from left to right. Then the ij are not available, not available, not available, not, oh yes, this is available. Then put it, put it into that bin. Pretty easy. Just looking at from left to right, oh, this bin is available, then, use it. Quite easy. Of course. Of course, if no such bins exist, no bins are available, then of course we open a new bin. We open a new bin, B, k plus 1, and of course put the current item into that new bin, of course. This is one, we have one important assumption. That is, of course, this is quite obvious, but each item cannot be divided into 2 or more small parts. That's exactly what happens here. If you put 0.5 and 3, then the remaining space is 0.15. So that's not enough for 0.25. What I'm saying is that it is not allowed to divide this item into smaller 2 parts. It's not allowed. It's just like to break your luggage into that. Okay, so it's not impossible. It's impossible. Okay. Now what? Now what? Okay. So that's ours. So now we are getting to the important point. How good? Okay. Now the question is, how good is this algorithm? That is why we'd like to introduce approximation ratio. This is exactly like competitive ratio. Okay. This is exactly like competitive ratio of online algorithms. Actually, no, the name is not so important. Some people say, some people also use the competitive ratio for this approximation ratio. Oh, well, the name is not so important. But anyway, this is a measure, our measure. Okay, what is that? Okay, what's that? Now I have a definition. Okay, now we have an important definition. Approximation ratio of algorithm A is R if and only if. It's the definition. If and only if okay. Approximation of algorithm A is R if and only if algorithm cost is at most R times optimal cost. At most R times optimal cost plus constant C. Plus constant C. This is this is not very important, but it makes things much easier. So we use constant C. This approximately means okay. So this approximately means optimal cost. Okay. So if the cost goes infinity, so if you consider big size problem, then we can now you can now ignore this constant C. That means algorithm cost over optimal cost is almost R. Oh, this is a reasonable definition of approximation ratio. Okay. Now theorem. Okay, now theorem. Our algorithm, first fit, has an approximation ratio of at most 2.0. Okay, that means this value is at most 2.0. Means the cost of FF, the number of beans used by FF is at most twice. At most twice the optimal number of beans. Okay? Okay. The number of beans by FF is at the most twice the opt beans. Proof. Sorry. Okay. I'm going to show that when first fit is finished, if we put all the items into bins, there is at most one bin. At most one bin that is at most half full. At most half full. All the other bins at least more than or at least one half full. Okay. Why? Why? So, for contradiction, suppose that there are two such bins. After if we finished, we have two such bins. Such bins means at most one half full. So we have open bins. Now this is a half. This is a half line. This is a half line. This means more than half. X is less than half. And Y is also less than half. Or at most one half. Sorry, at most one half. Okay? So suppose that there are two such bins. That means at most one half, that is X and Y. Okay? Then, we can imply a contradiction. Okay. Now consider the moment when the second bin, namely Y is opened. Now Y is opened. So some item I just comes to this new bin. But this is a contradiction. Suppose that this Y is now opened by item Y. But this is already contradiction. Why? This guy should have put here. Okay? Because remember FF. FF just looks at bins from left to right, then puts the current item into the first bin, which is available. This guy is available here. What's a contradiction? Item I should be put into bin X. What is a contradiction? Okay. Now, okay. Now let M be the number of bins used by our FF. Then so now the situation is not, this is not the situation. Okay? So your bins, we have M bins. M bins. And all bins but one. All bins but one are more than one half. More than one half. This is the situation. We have M bins. Then the total amount of items. Okay, the total amount of items. It means total amount of all items. Total amount of all items in the bins is at least the following value. Okay. Okay. So the total amount of items in the bins is at least, we have m minus 1 bins, m minus 1 bins, that is at least 1/2 plus epsilon. That is more than 1/2. And only one bin, which might be less than 1/2, should be this value, at least this value. Because if this x, this value x is too small, is smaller than this value, then of course all those guys can be here. So it's again contradiction for the same reason as before. So the remaining one bin that might be less than 1/2, but should be at least that value. After that, it's a simple calculation. Just a simple calculation, and the total value of the items is m/2. m/2. That means any algorithm needs at least this number of bins. Clear? Because the total, the size of the total, the sum of the all values of items is this value, at least this value. Then, because each bin has the size of 1, so we need at least this number of bins. That means FF need M. Optimal value is at least this value. That means approximation ratio is at most 2. Clear? Okay? I hope so. Good. So we are done. I'll show you some bad example. This is a kind of mean, example, the exact adversary of one-line algorithm. Okay. So third example for FF is okay. So we have 18 M items. We have 18 M items. M might be a big number. 18 M items. Each size of each item looks like this. So 1/7 plus epsilon. We have 6M 1/7 plus epsilon items, and 6M 1/3 plus epsilon items, and 6M 1/2 plus epsilon items. Epsilon is a small positive constant, of course. Know that 1/7 plus 1/3 plus 1/2 is less than 1.0. Yeah, just trust me. Okay. That means the optimal value is 6M. Because we can put this guy, this guy, this guy into one bin. So we need 6M bins. But Okay. What does FF look like? What does F look like? So FF, works. FF works like as follows. Put into this bin, this bin, this bin. No, this guy into the same bins. Then we can put six items into one bin, right? Because 1/7 plus epsilon. Epsilon is positive value. So we can't put 7 items. So we can put 6 items into one bin for this group. So that means we need m bins for the first group. For the second group, we can put 2 items into one bin, right? That means we need 3m bins. For the last group, we can put only 1 item in the bins. Remember, we are now doing fast fit. So, after, putting those items, the first bins are pretty full. Okay, so 1, 2, 3, 4, 5, 6, 7 items. Okay, so the first group. The second group is not very full. Something like 2/3. The third item is very unfull, only 1/2. Only 1/2. But now we are doing a fast fit. That means, from looking at the bins from left to right, then, for example, after the second finished, we can't put this item into any of these bins, right? So that's why the first bit, it needs m, 3m, 6m is equal to 10m. So the ratio over the optimal value is something like 1.7, 1.67. Pretty bad. But, just notice that it is still better than 2.0. 2.0. Actually, we have another theorem. We can prove that approximation ratio of fast fit is at most 1.7. Proof? Very difficult. Of course, that I want to get into the details. Very difficult. And of course, you can create even harder examples. So this value might be going up 1.678 or something like that. And the approximation ratio of the upper bound is also, I think, the current best value is a little bit less than 1.7. But still, there is a small gap. There's a small gap between the upper bound and the lower bound of the approximation of fast fit. This is a very kind of a natural problem. And also the algorithm is very natural. So for more than 50 years, people were trying to get, to narrow the gap, to make the gap smaller and smaller and smaller. Today, the gap is very, very tiny, but still we do have a gap. So if you can prove that there is no gap, you can prove true upper and lower bound of this approximation ratio, then this should be a very, very nice result. Yeah. This is a kind of a 50 years old, maybe 60 years old problem. So we still have many this kind of difficult problems even now. Yeah, in this field. Okay, good. In the next week, I'll show you another 3 or 4, another several examples of approximation algorithms. And the approximation ratio is sometimes very low and sometimes very high. Yeah. Okay, so see you next week.